All right, we'll go ahead and get started. Hello, everyone. My name is Maya Fernandez, and I am the Associate Director of Undergraduate Programs in Women's Engineering. Thank you for joining us today for this special session. Before I introduce today's speaker, I ask that all attendees please mute themselves during the session. Please include any questions that you have for Professor Armani using the chat feature below. We will have 10 minutes at the end of her presentation for Q&A. Professor Andrea Armani is currently the Ray Arani Chair in Chemical Engineering and Materials Science and the Director and the Director of the John D. O'Brien Nanofabrication Laboratory. She currently teaches Engineering Academy and MASC 350L, a nanofabrication laboratory. She received her BA in physics from the University of Chicago and her PhD in applied physics with a minor in biology from the California Institute of Technology. Professor Armani has received several awards for research and mentoring, including the Presidential Early Career Award for Scientists and Engineers. And she was named a Technology Review Top 35 Innovators Under 35 and a Popular Science Brilliant 10. In addition, her dedication to mentoring the next generation of scientists and engineers has been recognized with the USC Mellon Mentoring Award for Undergraduate Mentoring and the Hannah Riesler Award for Mentoring. Take it away, Professor Armani.
Great, thank you very much for the introduction. And also, I hope everybody's having a good virtual parents weekend. I know this is a little bit different than normal, but exceptional times call for exceptional solutions. So today we're going to talk about all the different ways that the School of Engineering has really been trying to contribute solutions to these challenges, and specifically an approach that my lab has been pioneering, as well as take a brief side detour and talk about a couple of the engineering honors programs that Viterbi offers. I always tell the students, but I know a lot of times information that I give to the students doesn't always quite make it to the parents. So I like to give the message to the parents as well, just to make sure that all of you know the opportunities that your children are being given, just to try to give information as many different ways as possible. Also, before we get started, I always want to thank everybody in my research group, because while I may lead a research team, the researchers are the ones that actually do the work. And my research group is comprised of a team of PhD students and postdoctoral scholars, as well as 9 undergraduate researchers. And they're the ones that are putting in the long hours to actually make the research successful. So I always want to thank them at the front. So today we're going to briefly talk about some of our work in UVC disinfection and developing a portable lightweight system to accomplish this, and talk about some of the results from that, and then move on to talking about the engineering honors program, specifically 2 different honors programs. So the first is the NAE Grand Challenge Scholars Program, and the second is the Viterbi Honors Program. And they're both very different, but they offer students 2 different paths to get an honors degree. So first, taking kind of a step back, thinking a year ago, when you're thinking about our healthcare ecosystem. And normally we would have kind of a hospital and maybe some local community healthcare centers, and companies and industry would design and produce materials and supplies needed by these different healthcare ecosystems. And the demand could be easily met by the industry. However, in the spring, it became apparent that the demand was not going to be able to be satisfied by the conventional industry manufacturers, either due to lack of supplies, in other words, raw materials, or due to the disruption in shipping. And so this is when suddenly the engineering community, and by engineering community, I mean both academic engineering community as well as kind of a kind of more general engineering maker community, kind of at-home maker community, really kind of stepped up and started developing new ways to either make PPE, clean PPE, as well as at-home developed instrumentation. And this kind of has revamped a lot of the approaches for healthcare. But in order, I'm just going to do this, in order to really think about how to clean a surface, you first need to understand how a virus actually infects a cell. So the super simplified explanation of how a virus infects a cell, you have a virus. It finds a cell that it wants to infect, and the proteins on the surface of the virus bind specifically to markers on the surface of a cell. Because it is bound to the surface of a cell, a process called endocytosis is able to happen. In this process, the viral RNA, as well as some additional proteins, are able to be internalized into the cell. At this point, the RNA is able to be converted into DNA, and then that DNA is able to be integrated into the cellular DNA. So now the cellular DNA has been modified. There we go. And at this point, the cell begins to replicate those surface markers that are present on the virus on its own cell surface. And the viral RNA has been replicated by the cell as well. So the viral particle can be reproduced by simply allowing the RNA to get re-encapsulated in the cell membrane and released. However, because that cell's DNA has been modified, the cell gets sick and dies. So now you have replicated the virus particle and killed a cell. And this process can just keep happening over and over and over again. So when you're trying to develop a way to disrupt this process, you can think about several different kind of steps along this chain where you might, target these distinct points, right? So you could think about trying to disrupt when the virus identifies the cell, right? So if you disrupt that identification process, then the virus won't be able to infect the cell. If you disrupt that internalization process, right? So if you do something to the viral membrane such that it can't actually be absorbed into the cell, then that would also inhibit this entire process. Similarly, if you disrupt that RNA transcription or how it's actually converted from RNA to DNA, that would also disrupt this entire process. So those are kind of three standard targets for how you can actually disrupt viral replication. So that's either addressing it kind of at the molecular or RNA level or at the more structural level. And those are kind of the three standard routes. So you're either looking to disrupt that S protein, so that's the protein on the surface of the virus, the membrane protein, or the RNA of the virus. And those are kind of the three approaches you can take. And there's different strategies, but they can be kind of simplified into thermal, chemical, and radiation. Thermal is basically heating a surface. There are lots of different ways to heat a surface. The typical way you think of is, putting something in an oven, but you can also do combinations. So you can imagine if you take something, put it in an oven, as well as, add a lot of humidity, then that will basically activate the virus and make it even more unstable. So by adding multiple mechanisms, you can enhance your ability to destabilize that viral particle. Then there's chemical, which is by far the most popular. Chemical is what the Clorox bleach wipes fall under. It's also what peroxide wipes fall under. Chemical is one of the most robust approaches, simply because it both targets that spike protein, that S protein on the surface, as well as the membrane. Additionally, chemical approaches usually involve some sort of physical strategy as well. In other words, you have to actually rub a surface. And whenever you're rubbing a surface, that's, you're going to be a little bit more aggressive than just relying on a heat treatment. And then the third approach is radiation. And radiation can take two forms usually. It's either going to be microwave or UV. And microwave is a specific frequency, right? And UV is a different frequency of radiation. And so today we're going to focus mainly on UV, but if you have other questions at the end, or I guess during, although I'll have to rely on my wonderful suite of students and staff to help me if there are questions during. So I'm going to trust them. I'm happy to answer questions during, though. I should have said that. Okay, so just as a quick refresher of DNA and RNA, because I know many of you might not have taken biology for a couple years. So the difference between DNA and RNA is really just the base pairs or the building blocks. DNA is double-stranded, RNA is single-stranded. They both have specific base pairs. They both are made of purines and pyrimidines. They both have adenine and guanine. RNA has cytosine, as does DNA, and RNA has uracil, whereas DNA has thymine. So they both have 4 base pairs. It's just which combination of 4 base pairs. So the reason why this is important is because UVC attacks specifically the pyrimidine base pairs. So it's going to attack both DNA and RNA, which means because DNA is in things like bacteria and RNA is in things like viruses, UVC will basically be, equally effective for both types of organisms. So how it works is UVC, when it's incident upon a surface, it is absorbed by either the RNA or the DNA. As part of that absorption process, it causes the disruption of the normal base pair binding that you would see, and instead of, adenine and thymine binding, that actually causes thymine to bind with itself. This is called something called dimerizing. And because of this dimerization process, you now end up with your backbone, instead of being, a nice helical shape, it has kinks in it. And due to these kinks, it can no longer replicate. So if you think back to, the 3 different strategies of how do you inhibit viral replication, one of them was to inhibit the replication or the conversion of RNA to DNA. And so this process will inhibit that replication. So it stops that fundamental biological step. So it's very straightforward in its mechanism. Using UVC has been in healthcare. It's been around for a while. So it's typically been used in small, I call them toaster oven type size systems. They literally have a shelf in the middle. You put something in, they have lamps on the top and bottom, just like a toaster oven has heaters on the top and bottom. And they can hold something, about the size of a toaster strudel. But they're, so they're designed, they're optimized for small things. And then they're also used in research. So the thing that looks kind of like a large cabinet, something called a biosafety cabinet. So you usually will culture cells in them. So you want them to be very sterile because you don't want your cell cultures to become, infected with bacteria. So usually what happens is you will perform a biological experiment, and then you'll turn on a UVC lamp as you walk away, and you will just keep your UVC lamp on when you're not in use of the system, just to keep it clean. In the last year or two, more autonomous systems have been developed. And an example is the robotic system. So this is kind of the equivalent of a Roomba plus light bulbs. So it has a base that can move autonomously or semi-autonomously around in a space. And then the light bulbs, which are vertically mounted, are able to expose the space to UVC light. So there's obviously, with the first 2 systems, a person who is nearby won't necessarily get exposed to high intensity UVC light. So the first system, the toaster oven approach, right? You close it, even if a person's nearby, they're going to be protected from UVC. In the second system, due to the way that the light is mounted, the person is going to be protected. In the robotic approach, the light, it can go in any direction. So if you approach the robotic system, then you can be exposed to UVC. And this is very important to recognize because UVC, at least at the wavelength that is germicidal, so 260 or so nanometers, has been linked to cancer, blindness, so a lot of diseases that are, or can be worse than a viral or bacterial infection. So it's important to try to balance the need to clean a surface with, also preventing additional diseases from the cleaning method. So moving back to think about our healthcare ecosystem. So under normal circumstances, usually in a healthcare center, so something like the Keck Medical Center, you will have kind of a centralized spot within the hospital where all types of sterilization procedures are performed. And this could be thermal, chemical, radiation. So all types of unclean material is brought to this centralized site, cleaned, and then again, redistributed. And this process is very effective because a lot of the techniques used, especially the chemical ones, will generate a lot of chemical waste. And so having a centralized spot for this type of process allows for centralized chemical waste handling and facilitates a lot of logistics. However, recently, that type of approach hasn't worked simply because of the quantity of PPE that we've needed to clean and the quantity of waste that we've been generating. So this has led to hospitals creating a decentralized strategy. And in the decentralized strategy, they obviously are still relying on that centralized site, but then they have secondary locations which can perform kind of like quick clean approaches. And just to try to bring this into reality a little bit to give you an idea of what I mean. So these are examples of field hospitals, and these are all over the world. This isn't like a US thing. So these are field hospitals that obviously will need to be able to clean and reuse, whether it's surgical tools or PPE or face shields or face masks for ventilators, but they need to be able to reuse them on site. They can't constantly be carting them back and forth. So they need some way to do sterilization on site. And they can, for some parts take them back to a primary facility, but you can imagine on a day-to-day basis when you have like 1,000-person hospital bed, you can't constantly be carting that level of materials back and forth to a main hospital. So it would be for a facility like this where you'd want to have kind of a secondary on-site way of cleaning materials. So it was with that in mind that the CEO of Keck in March basically reached out to a lot of the engineers in the Viterbi school and asked for help, actually kind of at two levels. The first was just if we would give them all of our gloves and face shields and face masks and everything we had and goggles. And then the second was if we'd be willing to help them. And one of the questions that they asked for was if we would be willing to help them make different ways of cleaning PPE. And so UVC was one of the challenge problems that was posed. And the design rules that were given to us were fairly straightforward. We needed to be able to achieve over 100 millijoules per centimeter squared in dose. And this is the standard dose that little toaster oven gets. It needs to be lightweight and portable so that it could be moved to one of those like secondary off-site locations, as well as moved around within a hospital. So it needed to be easily adaptable. And then inexpensive, also have flexible components, because if you think back to like March and April, there were a lot of shortages around the country. And then it also needed to work. Obviously, big design criteria. So we had to be able to verify that it worked with model organisms. So our first approach was basically to take, a bin and put a UVC light in it. And we sourced our light from a manufacturer. And then we mounted it and we tested to see exactly what the intensity was inside of our bin. This is clearly lightweight. It's a plastic bin. It weighs about 4 pounds. And then, after doing like a quick thought on this, we realized that if we added a reflective coating inside of the bin, it would both help with keeping the light inside and better confined inside of our container, which is good from a safety perspective. It would also help basically amplify the light inside of the cavity because it forms something called a Fabry-Perot cavity, which is a specific type of optical resonant cavity. So you can think of it like the optical analog of an acoustic tuning fork. So instead of having the light only bounce back, it basically oscillates back and forth, bouncing on and off those reflecting walls. So this allowed for an amplification of that single light bulb. So it was more effective and more efficient. And we chose to spray paint the inside, which is both inexpensive and effective at creating a very uniform coating, with chrome spray paint. So chrome spray paint is actually comprised of aluminum, and aluminum is about 85% reflective in the UVC wavelength range. So it's very reflective in terms of having efficient reflection of the UVC light. And we can buy it easily in LA. So we did a little bit of modeling, of finite element method modeling, on the actual light field distribution inside of our system. And we didn't just look at the optical field distribution, we looked at, I have two dogs, I'm sorry if you can hear them. So we have we did 3 models, one where we just ignored the fact that we had that coating, one where we kind of gave like a low end, so we assumed that the coating was only 25% reflective, and one where we did like kind of the high end or the ideal version, so it was 85% reflective. And we also assumed that it had a 1 minute total exposure. So this kind of gave us, so the 0% reflectivity, obviously, we were not able to hit. I'm gonna be right back. The mailman. Every dog's arch nemesis. Okay, so as I was saying, hopefully they'll chill out a little bit now. Okay, so we assumed 1 minute of total dose, and at 0%, okay, at 0%, we were barely able to hit that 1 millijoule per centimeter squared. But by the time we had 25% or 85%, we were well over that ideal dose. There we go. And in our system, we were using a bulb that was 15 watts, but we wanted to kind of do a little bit of comparison on if we had a lower power or higher power bulb. So we also did some calculations with both lower and higher power bulbs. And if we had a lower power bulb, we were going to be able to hit the minimum needed power with about 40 seconds, 45 seconds, and higher power bulb, it was going to be in about 20, 22 seconds. So it wasn't really that big of a difference because we wanted to start our experiments at about a minute. So either way, either optical source, a minute was going to work. And just for some actual comparisons with lots of other different types of viral pathogens and bacterial pathogens, if you look at things like anthrax, which everybody always thinks of as being the worst possible organism. So if you look at anthrax and E. coli, they actually have higher sensitivities to UVC, in other words, lower thresholds to UVC than an adenovirus, which is actually one of the hardest organisms to kill with UVC. But all of them are at or below that 100 millijoule per centimeter squared threshold level. So that was how that level was determined. So in our initial experiments, we were focusing on being able to clean face shields, and this was part of a larger USC effort. So there was a group out out of Annenberg, kind of a team effort out of Annenberg and the Iovine and Young Academy and the architecture school that was working on doing 3D printing of face shields. And so they were supplying Keck with thousands of face shields, but obviously you don't want to make a plastic face shield only to throw it away after you wear it, you know, for a day or two. So Keck wanted to have a way that they could actually reuse the face shield. And so our goal was to develop a system that would allow them to reuse the face shields. So we wanted to test the efficacy of our system on actually cleaning the face shields. So in order to do this, we didn't necessarily want to take one of the face shields and cut it into a bunch of little pieces. So we looked around for what is an equivalent material, and it turns out that the plastic Petri dishes we had in the lab that were already sterile were made out of the same plastic. And then we tested them with a model organism, and we used an organism, Bacillus cereus, which is gram-positive and endospore forming, and those two terms are really important. So gram-positive means that it's very hardy. It's the easiest way to describe it. And endospore forming means that when you take it out of a liquid environment, it actually forms a really hard shell around it, which makes it even more resistant to UVC. So that's one of the things that anthrax does, is it forms a really hard shell around it to make it really resistant. So we verified our bacteria using something called MALDI, just to make sure that we had what we thought we had. And then we performed a whole suite of studies. So we looked at the dose dependence, we looked at the location dependence, because if you remember on the modeling, if the sample was in the middle of the box, it was going to get a lot higher dose versus if it's on the edges. So we looked to see if we could actually detect that difference. You know, we basically wanted to say, you know, worst case scenario, if someone managed to take a face shield and shrink it down to be the size of an ant and put it in the corner, like, would it still work? So we wanted to look at all the different extremes. And then after exposure, we scraped the bacteria, all the little endospores off the plastic Petri dishes, replated them onto agar, so basically bacteria food, incubated them in a nice cozy incubator and with lots of humidity at the right temperature for 24 hours to try to encourage growth, and then went back and counted to see exactly how many, they're called colony forming units, so basically how many growth clusters we actually had. So this is a summary of the data. So the top one is when we had no treatment. In other words, we just plated it first on a plastic Petri dish and then scraped it off and then put it on the agar. So the top one verifies that our bacteria was in fact alive and was able to replicate in our incubator, and it was able to replicate really well. It was very healthy bacteria. And then the bottom one is after we exposed it for a minute. So there was nothing. The black stuff that you can kind of see, that was actually just writing on the back of the Sharpie marker so that we could keep track of which sample was which. So that's not bacteria at all. But in summary, looking at the actual chart, on the far left, starting when we had no treatment, we had over 1 million colony forming units, so basically significant growth. If you get anywhere over 1 million, it actually begins to get hard to count, simply because they, as you can see here, they kind of begin to interact with each other and it gets challenging. When we exposed for a minute, depending on where it was located within the box, if it was in the middle, actually if it was in the middle at 1, 3, or 6 minutes, we never saw any growth. If it was on the edge, we saw a little bit of growth at 1 minute. And then if it was on the other edge, we saw a little bit of growth at 6 minutes. And this could have been just exactly where it was located on the edge. But basically, independent, we always saw more than 3 log reduction, which is what the goal was and the standard was set by the CEO of Keck. And that standard was actually set by the FDA, he didn't just make it up. So the lingering question is always, you know, does UVC impact filtration ability? And this is a general bigger picture question, because there's lots of technologies looking at using UVC as a way to clean N95 masks. So what is the impact of UVC on masks? So we're fortunate. So we live down the street from Caltech, and they actually have a system that can test filtration efficiency of masks. So we took a pair of N95 masks and put them on their filtration tester system, which is actually a dummy that you can really make sure that there are no holes in the fit. And then you can control both the size of the particles that are being exposed as well as the flow rate of the particles. And so you can really look for any kind of fluctuations in filtration efficiency as well as flow rate, as well as leaks of particles. And you can do this over and over again and expose the mask and then remount it and look for changes. So we did a pair of measurements, and we used KN95 masks because, again, this was in April. So the first measurement, the first actually suite of measurements, we would first expose the mask for 3 minutes, then take a measurement and then repeat it. And we did this 40 times. So basically looking at, repeated use of UVC to clean a mask. And then for the second measurement, we took that same mask that we had already exposed 40 times and just did one really long continuous exposure. And the motivation for the second measurement will become really obvious. So basically, after doing a bunch of short measurements, nothing really changed. In fact, the filtration actually got a little better, which is probably just an anomaly. But even after doing the really, really long measurements, nothing really changed. And what happened is the PhD student got tired of doing the 3-minute exposures, because if anyone's ever done like a 3-minute experiment or made microwave popcorn, 3 minutes isn't long enough to actually do anything. So he was basically just standing there and staring and waiting for 3 minutes and then retaking the measurement, which is why he finally just like left it in there overnight so he could go home and sleep. So I feel really bad for Hassan. So I always want to give Hassan credit because he's super patient. But neither short or long-term exposure actually changed anything, at least at these UVC intensities. If you really increase the UVC intensity, you can damage the really delicate filtration ability of N95 masks. So there is a very delicate balance there. But at moderate doses, it's okay. But you really have to balance that. So it is a consideration. So where we're going in the future with this is we're working with like SK Gupta, who's an expert in robotics, trying to develop more active robotic type systems, not passive robotics. So integrating into a multiplex system that can do both chemical and UVC, as well as looking at integrating UVC into things like TSA screening systems, ductwork, so more complex and I would say interactive, but yet not interactive systems. And then I briefly want to go through the engineering honors program unless there are questions. If not.
No question.
Yeah, okay. So there are two honors programs at USC. There's the Grand Challenge Scholars Program and the Viterbi Honors Program. And I'll explain what the two programs are and how they're different, and then also give a couple examples of projects, because they both involve projects. So I'll give a couple examples of projects that students have completed as part of the programs. So the Grand Challenge Scholars Program is part of actually an international program. So the Grand Challenge Scholars Program is part of the National Academy of Engineering, or the NAE Grand Challenge Scholars Program. And the NAE was actually founded by Abraham Lincoln, just as a side note, as an advisory board to give him advice on how to choose weapons during the Civil War. So it has a really, truly long history. But the Grand Challenge Scholars Program is a joint effort between the NAE of the US, the RAE, so the Royal Academy of Engineering of the UK, as well as the CAE, or Chinese Academy of Engineering of China. And the joint effort or joint vision is to try to train engineers, engineering students to be well-rounded So train them not just in academics, but also train them to be able to address societally relevant challenges in an ethical manner. So not just think about like the math of the problem, but also think about challenges more holistically. And so the only way to really do this is to, make them face, these types of holistic challenges in an academic setting, so they can kind of begin to think through them and think through the impact of their actions early on. So to be a Grand Challenge Scholars Program participant, you have to look at 5 different things: entrepreneurship, research and creativity, social consciousness or social awareness, cultural awareness, and multidisciplinarity, which basically means you have to do something outside of your specific field of engineering. These are a few examples of ways that students can demonstrate this. So for engineering creativity, this could be a research project, or it could be engagement in a student club. So one of the more popular student clubs is the Rocket Propulsion Lab, or RPL. So RPL is entirely student run, and every year they build a rocket and launch it. Not last spring, but the spring before that, they actually broke the Common Line, which is one of the, it was the first time that an all-student team actually accomplished this. So it was a huge achievement for RPL. They had great goals for this last spring too. It's very painful. Okay, so then for entrepreneurship, there are a lot of startups that come out of USC. So a lot of students will, participate in things like the Massey Entrepreneurship Prize. They can participate in the Viterbi startup. There's the Fab Lab, and then most recently this past year, students who were members of the Grand Challenge Scholars Program could also engage with the NAE COVID-19 Fast Action Cell, which was basically a nationwide challenge to try to come up with solutions, whether they're solutions you could do at home or as part of a team, in response to COVID-19. And USC, specifically Giannis, actually took a leadership role in kind of launching that program. And I'm sure there's information available if you're interested in that. And then multidisciplinary, a lot of the ways that students address this kind of facet is looking at kind of integrated degree programs. So the CS Cinema program is one of the most popular ones. This is a really amazing degree program between the cinema school at USC and the computer science degree program. And students learn how to do graphic design as well as programming. And so that's really popular. Another way students can accomplish this is by being really actively engaged in something like a minor or a club that's completely distinct from engineering. So for example, by being involved in studio art or a symphony, something like that. And then cultural awareness. There are a couple ways students demonstrate cultural awareness. One approach is to be a member of like an iPodia classroom. Other ways include doing a summer abroad or being involved in something like Engineers Without Borders. So it's just to make sure that students are aware of things happening outside of LA, although LA is, it's a great place, very diverse. Social consciousness. So this is going to be designing solutions to global problems, not local problems. Burchin, who's a faculty member in civil engineering, recently launched a class specifically in response to this challenge. It's Civil Engineering 499. It's a design challenge, and students it's a 2-semester long class, and students spend 1 semester abroad so they can really get kind of hands-on experience in the environment where they're going to be trying to design a solution for a specific challenge. The first time they went to Greece to actually look at the refugee crisis there. And they designed solutions like water filtration, housing, those types of solutions. So it's real world practical experience. And a lot of those are supported by the Min Family Challenge. And then there's the Viterbi Honors Program, which is completely distinct. So the Viterbi Honors Program, the point of the Viterbi Honors Program is pretty much every university, every engineering school has a classic honors program that is GPA and thesis driven. At Viterbi, we've taken this and kind of put our own spin on it. So ours is GPA based, but the thesis can either be a research thesis or it can be an innovation or entrepreneurship thesis. It has to be a written document, but it can be either in the form of a business plan if you're thinking of the innovation track, or it can be the more classic research thesis if you're doing the research track. So I'll go through a quick example of an honors thesis project as well as a Grand Challenge Honors Program project. Both of these are super fun. I'm much more excited about the first one because it's a current honors student in my lab, and I love Reese. So one reason why we're excited about this particular project is because it's taking the UVC system, but really focusing on the more longer term challenge, because there will be life past COVID. But antibiotic resistant bacteria has been around for a while and it will continue to be a problem. So a lot of the cleaning methods that we're beginning to see popping up now, they may stick around. And this was highlighted in a report from the CDC that came out in December of 2019, so almost a year ago, highlighting that more action is needed across settings, industries, and countries to fully protect people from antibiotic-resistant threats, simply because more antibiotic-resistant bacterial infections are occurring due to community spread as opposed to occurring from healthcare settings. So her honors project, Reese's honors project, is basically to redesign the UVC system to be even lighter weight, to be collapsible, to be something portable, and to require even less power, and to ideally be effectively indestructible. So obviously, if you have something based on a 18-inch long glass light bulb, that's not gonna fare well if you want to crumple it into a little ball and put it in a backpack. So we want something that's a little bit hardier than that. So those are the project goals. And she's working with a BME PhD student in my lab, Lexi. And one of the benefits of doing the honors research track is usually undergrads are paired with PhD students as mentors, which gives them a lot of one-on-one interaction, and it also gives them role models on the future career directions they can take. And that role model interaction is also really important for undergrads, especially engineering undergrads. So the existing one, right, was that box with the light bulb. And where we want to go with it is to have something that is lightweight, portable, collapsible. Ideally, instead of a light bulb, it has an LED source. It has integrated circuitry, control circuitry, has some sort of safety mechanism. And obviously, we still need to do the testing with model organisms. So far, and keep in mind, she's been at this for about 2 months. So, early stages. But she has a redesigned container. It's a collapsible fabric on the outside, mesh foil on the inside, so it still has that aluminum reflectivity on the inside. It collapses to be about 1 inch thick, but it still has the same volume as the original bin that we were using. And then she's working on doing an Arduino controlled system. And she's learned through this project, Arduinos, control circuitry, things like soldering of LEDs, and she's going to start doing the modeling of the actual LED and light distribution inside. And as a result of that, she's then going to figure out where she actually should distribute the light sources inside her new system. So that's the honors program thesis. The NAE Grand Challenge Scholars Project, these are usually more collaborative in nature, so they aren't a single student, they're a team. This specific Grand Challenge Scholars Project was actually part of a team competition. So every other year, there's a global Grand Challenge Scholars Summit, and it rotates between the US, usually in Washington, DC, the UK, London, and China, Beijing. So 2 years ago, there was a summit that was in London, and before the summit, there was a competition, so basically a pitch competition, and each country could send 3 teams. And the USC team was one of the 3 teams. Yay, go us. And this was the team. So their idea was to create a subsea communicator module that could basically connect the oceans and allow for communications from subsurface to the surface. And it could be used for, their idea at the time was really for natural disaster communications. So things like hurricanes in the Caribbean, when you need to search for people, when you need to search for wrecked boats, when you need to just search through wreckage, and it's not safe to take a boat into an area that's strewn with a lot of active wreckage. But you could send kind of a swarm of these robotic subsea communicators into the area to try to send information back. So that was their idea, but obviously it could be used in a lot of different applications. And they were a team of 4 Mechies and 1 EE. The innovation part of their system is really that it combined both optical communications as well as acoustic communications. So by combining both optical comms and acoustic comms, they were able to basically cover a huge range of communications, of basically distance, which would give them a huge advantage over only having a single modality. And they actually built a prototype and tested it, and they worked with a couple EE faculty on actually building the prototype and testing it. And then again, they were selected to represent the US. Giannis went with them to London. Our dean went with them to London to accompany them and make sure that they did well. They didn't win the global competition, but they still did a great job. So again, I just want to thank all of you, and if you have questions, I'm happy to answer them.
Thank you so much, Dr. Armani, for that presentation. So I will go ahead and monitor the chat here. I included some links to the Grand Challenges Scholars Program, the COVID Call to Action, and also the Engineering Honors Program. So please feel free to share those with your students. Also feel free to unmute yourselves as well. That also works.
And Rick, yeah, I think it was UPS. If nobody has any questions, I can answer questions on other things too. I'm open. If not, you can go hang out with your kids, because I'm sure you don't see them enough.
Also, I just want to remind everyone about the Table for 6 mixer following this event at 4 o'clock as well.
I was gonna say, or you can go see the sun. I gave my freshman recess and told them to go see the sun in class on Tuesday. Okay.
All righty.
I will let you all go. Okay. Have a great evening, and make sure you go meet Giannis.